All right, let's continue with our talk of semiconductor materials. Okay. And so I believe we stopped here. Energy band gap. Okay, so this is a two-dimensional illustration of the silicon lattice structure. We have silicon atoms bonded with neighboring atoms. Each of the lines that you see between the atoms represents a covalent bond, and each of the dot represents an electron. Okay, so at absolute zero, meaning at 0 Kelvin, actually it's not okay, let's write down absolute zero or 0 Kelvin. Excuse me, all of the bonds are intact. All of the electrons are in their spots or in their spaces, and there are no free charge carriers. As the temperature increases because of the acquired thermal energy, some of the covalent bonds are broken. Some electrons acquire enough energy that they're able to break free of their bonds and are now freely moving around in the lattice structure. And so that right here is the representation where a bond is broken. Okay. Broken bond. It's a broken bond. So when an electron moves out, we have an empty spot left in its place. Electron leaves, results in an empty spot. And that empty spot is known as a hole. The empty spot is known as a hole. Now, as the electron moves through the structure, because there are a large number of electrons that have come out of their spaces, there are equal number of electrons and equal number of holes in the lattice structure. And then we treat the hole as a particle in its own right with positive charge. Okay, we treat it as a particle in its own right as a positive charge. And so we say electrons and holes, polar opposites. So how do holes move around in the structure? Let's say we have an electron here. And then we have, it moves to another spot. It's going to leave behind a hole in its place, which would be that. The electron moves here. This was an empty spot left behind by some other electron. Then it could move to another spot. And I'm drawing this in one row, right? Electrons just moving linearly row, but inside a silicon lattice structure, I mean, it could just be random. The movement could be up, down, left, right, any direction. And so as the electron moves towards the left, in this case, it's moving towards the left. Now, the reason it was able to move is because there's an empty spot in that place. So as the electron moves in one direction, the hole is now getting filled up. And so the hole is moving in the exact opposite direction. And so where there was an empty spot here on the far left, that empty spot is moved here. And then it's moving one more spot to the right, and it's moving one more spot to the right. And so as the electron moves, the hole moves along with it. And so both particles are now propagating through the lattice structure. All right. This will be the electron flow in this direction. And this will be the hole flow in the opposite direction. Let's take a pause, think over it. Let me know if you have any questions. Any questions? Okay. All right. So these electrons and these holes that are generated are already present in the silicon, right? They are part of the silicon structure. So they're intrinsic to the material. Hence, these are known as intrinsic charge carriers. They carry charges. Electrons carry negative charge, holes carry positive charge. So they are charge carriers. And because they're already present in the silicon material, they are known as intrinsic charge carriers. So intrinsic charge carriers. Yes. Yes. Yeah. So all of these electrons, whether they are in place or they have moved out of place, they are already present in that silicon material. And so they are intrinsic to the material. We are not introducing any external impurities at this point. They're already present in that silicon lattice structure. And hence intrinsic charge carriers. And so this semiconductor material is also known as the intrinsic semiconductor. Okay, intrinsic semiconductor. These charge carriers are generated because of thermal effects, because of acquired thermal energy. Okay, acquired thermal energy. We are not applying any external fields to it. There is no other external energy sources. We are not talking about shining light on it. We are not providing any external voltage, external current, external electric fields. It's the material sitting at room temperature by itself. So if there's a piece of material, silicon material sitting at room temperature with no other factor except for room temperature, means thermal energy relative to absolute zero, we say that the material is at thermal equilibrium. Okay, we say it is at thermal equilibrium. If it is at thermal equilibrium, then the numbers of electrons and the holes that are present are exactly the same. They're equal in number. So every electron that moves out, we have a hole that is generated. So electrons and holes are balanced. So a state of equilibrium exists. And it is referred to as thermal equilibrium. Okay. Yes. Yes, this is just thermally generated. We are not applying any external energy. The only energy that is being forced on the material is thermal energy, temperature effects. Yes. So repeat your question again. Okay. Oh, so okay. So the question being asked is, wouldn't thermal equilibrium exist at any temperature? Am I understanding it correctly? Okay. So in a manner of speaking, yes. Yes. The answer would be yes. Because even if it's at, let's say, 100 Kelvin, then the number of electrons and the number of holes that are generated are exactly equal. So if you're talking about 100 Kelvin, you would say, yeah, the material is at thermal equilibrium. But 100K is, generally speaking, in our world, in the environment that we live in, temperatures would be, and you say room temperature environment would be about 25, 27 degrees C or 300 Kelvin. And so we say that would be thermal equilibrium at that temperature. Doesn't matter what the temperature is. Thermal equilibrium simply implies that we are not applying any other energy source to our semiconductor material except for temperature, except for thermal energy. So the only charge carriers that are present in the semiconductor is because of thermal energy, and hence thermal equilibrium. So electrons plus holes taken together are labeled as an electron hole pair, the electron hole pair. So electron moves out of its spot, leaves behind a hole. So it's an electron hole pair. Also, from this pair, oftentimes it also happens that electron can jump or move into a spot, which we just spoke about, right? So if that happens and the movement of that electron stops, obviously if an electron moves in an empty spot, it can keep going further. But let's say if an electron moves in an empty spot and then stops, what happens then? The process is known as recombination. And when that happens, one negative charge is out and a positive charge is out. So you lose charges. So an electron hole pair is now taken out of the structure. Okay. And we are talking in terms of free charge carriers, right? As long as the electron is moving around, it is free to carry charge. It is free to conduct electricity. But as soon as it jumps into a spot, a bond is established, negative charge carrier is out, and so is a positive charged hole. So recombination, meaning it results in a positive and a negative charge being taken out of the equation. So this process is known as recombination because they recombine. They recombine and a positive and negative charge vanishes. In the process of recombination expends energy. The excess energy is dissipated in the form of heat or light. Okay, heat or light. All right, so how many charges or how many electrons are generated? Well, we have an equation for that. We represent the number of electrons with n, so this is the number of free electrons that are generated, and we represent the number of holes with the letter P. With the letter P. Yes. Yes. It's going to be the next point, actually. So the question being asked, what is Ni? And so Ni is basically the number of intrinsic charge carriers present in a semiconductor material. So by its very definition, N would be equal to P. Number of holes is equal to number of electrons. And that would be equal to Ni. Now I want to distinguish between N, the number of electrons, and Ni is simply the number of charge carriers. Ni could represent both N as well as P. Okay, N is for electrons, P is for holes. But Ni represents both P as well as N. And so Ni is the number of intrinsic charge carriers. Intrinsic charge carriers. And the equation for that is given right here. Ni square is Bt cube e raised to minus Eg over Kt. And now let's break it down. Okay. Ni, of course, we already established or defined as the number of charge carriers. B is a material dependent parameter. It's a material dependent parameter. It's a constant that is known to us. And it actually represents the effects of temperature on the lattice structure. Okay, so that material dependent parameter is different for different materials. For silicon, B is equal to 1.08 times 10 raised to 31 K raised to minus 3 times centimeter raised to minus 6. Okay, that is different for different materials. Next slide, I have a small table which gives you the parameter for silicon, germanium, and gallium arsenide. Yes. Yes. If you want Ni, you simply do the root of the above equation. So in a quiz or an exam, I might ask you, what is Ni? Okay, what is the intrinsic? If I just use words, what is the intrinsic charge carrier concentration? You can find Ni square is whatever the number is. But if I ask you specifically what is Ni, then you have to find the square root of that value. Okay, so please keep that in mind. I might simply ask you, what are the number of electrons in there? What are the number of holes that are generated? No. So the question being asked is, would Ni be the sum of N and P? The answer would be no. Now, Ni is N and Ni is also P. Because every N, meaning every electron, is balanced by a hole. So at any given point in time, if there is an electron or free electron, there is also a hole accompanying that electron. For an electron to be free to move around, by its very definition, it means an electron has left it's broken its covalent bond and it's moved out of its spot. So by its very definition, it's free to move around. It's moved out of its spot. That means there's a hole in its place. So one free electron is always accompanied by one hole, one positive charge. So Ni is equal to N and Ni is equal to P, but it's not equal to N plus P. Good question. So again, Ni is the square root of the equation above. B is the material dependent parameter. T is the absolute temperature in Kelvin. Again, remember, intrinsic carriers are generated due to thermal effects. So the temperature is a critical factor. E exponent raised to Eg, which is the energy band gap, so the band gap energy in electron volts, and K is the Boltzmann's constant, electron volts per Kelvin. And you have to be careful. The reason we are using Boltzmann constant as electron volts per Kelvin is because we are dealing it in terms of semiconductor energy, semiconductor band gap, and the temperature effects per Kelvin, right? If you're used to using joules, right? Depending on the equation, we might just use joules. Then you'd have to multiply it something else. In the end, you would end up with this exact same value. Does everyone understand what I'm saying? Okay. Also, the reason it's in centimeters is because the number of atoms, this is Ni would be atoms per centimeter cube. So Ni is how many atoms, or how, sorry, not atoms, free carriers per centimeter cube. More appropriate to say particle per centimeter cube. So if you take a given volume, one given volume of cubic centimeter, that is the number of particles that are present in there. Okay. When you do your calculations, when you perform your calculations, I typically like to convert everything to meters. Okay. So if it's given to me in centimeters, I would just convert it to meters. Right. 10 raised to minus 2. Yes. Yes. It's a product of P and N. So the question being asked is, what is Ni square? Ni square is the product of P and N. P and N. Yes. So the question being asked is about this. No, this E is the exponent, E raised to minus Eg over KT. The exponent. Okay. Eg is the band gap energy, electron volts. That is a constant. B is a constant. K is a constant. The only variable in the equation is T, temperature. As the temperature increases, the number of electrons, or Ni, increases. As the temperature decreases, Ni decreases. Right? If you plug in T as 0, Ni is 0. Make sense? So again, the equation, we are not deriving the equation, right now. We simply need to determine the approximate number, and this equation is of course approximate. We cannot calculate it down to every last single atom, last single particle. So this equation will give us an approximate value of how many charge carriers are present at any given temperature in any semiconductor material. So in the book, there's an example. There's an example of silicon at 300 Kelvin. Please go through that example and perform the calculation yourselves so you can arrive at the same answer. Okay. Remember, we have the quiz coming up on Friday, and the Friday quiz will be on the material we have covered a little bit last Friday, then Monday, and then today. Okay. And then Monday, we will cover the quiz, the material that we have covered this entire week. So Monday, Wednesday, Friday. So Friday quizzes would be Friday, Monday, Wednesday, and Monday quizzes would be Monday, Wednesday, Friday. So all of this material is fair game for Friday's quiz. Okay. So please practice. And then the homework assignments also set. So since I'm talking about the quiz, I might as well announce the homework. The homework assignments, I believe 2 and 3 is due on 16th and the 18th or the 19th. Okay. So please be up to date in your Canvas calendars as well as on Connect. Okay. So what was I saying? So practice. And then, yeah, and then definitely be careful. Centimeter is to -6. If I'm converting into meters, 10 raised to -2 times 10 raised to -2, 10 raised to -2, so on and so forth. Otherwise, you would end up with the incorrect values. So that's why practice on your own calculators. All right, any other questions before I move on? Okay. All right, so here is the table, the material dependent parameter, as well as the EG values, the band gap energy values for silicon, germanium, and gallium arsenide. And since these are standard equations, right, you can calculate at any temperature. You already have a plot, right, chart of the intrinsic carrier densities at different temperature. Okay. As the temperature decreases, the carrier density decreases, right? As the temperature increases. So this is decreasing temperature, reciprocal of the temperature at 0, it should go to 0. Okay. Now we say that we have charge carriers, right? What can we do with these charge carriers? Since they're free to move around and they have the ability to carry charge or conduct energy, if we apply an external electric field, these charge carriers are going to drift in response to that applied external energy field or external electrical field. So charge carriers will drift in response to an external electric field, giving rise to a drift current. Anytime charge moves, we are saying energy is being transferred, saying electric current is now flowing through the circuit. The charge carriers drift in response to an external stimulus, to external electric field. Okay, external electric field. So this drift is termed as drift current. Okay, drift current. That current density J is defined as Q times V amps per centimeter square. Amps per centimeter square. Yes. The velocity of charge, yes. Yes. Electrons and then holes. And the next slide, we'll talk a bit more about mobility of electrons and holes. It's different for both. And there's a reason why. So we'll talk about that on the next slide. Okay. So again, even if you have an intrinsic piece of semiconductor, if you apply an external electric field to it, there'll be some movement in there. It's not as much as a conductor, hence a semiconductor, right? Now, mobility. Now, electrons are free to move about, right? They're free to move about in the silicon lattice, in the silicon structure, or the lattice structure. They can move anywhere. They do not have to occupy the spot. I mean, where the the covalent bond exists. But a hole is localized. a hole can only move where an empty spot exists. So electrons have higher mobility than holes. Okay, electrons have higher mobility than holes. Electrons are free to move around anywhere, so they have higher mobility. Holes are localized; they are moving from spot to spot in the lattice structure. Now, we can relate the velocity to the electric field. As the electric field increases, we would say the velocity would increase, just generally speaking, right? The more energy you supply, the higher your response. So when you increase the energy being supplied from the electric field, the velocity would increase proportionally, right? So it'd be proportional. To create an equation, we introduce a constant of proportionality in there. That constant of proportionality is defined as the mobility noted by the Greek letter mu, mu. Okay, so Vn, velocity of electrons is minus mu n times E. E would be the applied electric field. Vp would be mu p times E. And to balance out our equations, we put a minus sign in front of the equation for electrons for the negative charges. Okay. So again, Vn is the electron velocity, Vp is the hole velocity, and then mu n and mu p are the constants of proportionality that allow us to relate the velocity and equate it with the applied electric field. Yes. Both. So the question being asked is, I'm going to rephrase, why is electron mobility higher than holes, right? So yeah, that the biggest reason is, of course, because electrons are free to move around anywhere. Holes can only move from spot to spot. So a hole only appears if an electron has left its spot. But if an electron jumps into an empty spot, that hole disappears. So electron mobility is higher because they are not localized in the silicon lattice structure. But holes are localized. So mobility for holes is far less than the mobility for electrons. It both. So the question being asked is, are the holes simply appearing or are they actually moving? But then let's go back to this illustration that I made here. It's a hole appears, so the answer is both, because the hole appears because an electron has moved out. So if an electron moves out and is not occupying any spot, then the hole just exists in that place. But if there are, let's say, for instance, 100, well, not 100, but let's say 10 electrons have moved out of their spots, out of thousands, right? So if 10 electrons have moved out, now we have 10 empty spots. Out of those 10 empty spots, let's say 5 of those electrons move back into those spots. So those 5 holes have disappeared now, leaving behind 5 electrons that are freely moving around, but those holes are localized. If an electron from some other part of the lattice structure jumps into that hole, now that hole, which was here, right in front of me, is like maybe, over there, which, 10 feet away. I'm just throwing out numbers in here. So an electron has moved out from there and has jumped into this hole, but then this hole has now appeared there. So it's appeared, but we also treat it as a particle in its own right. So we say it has moved from here to 10 feet away. Does that make sense? Right? So it appears there, but to make our calculations easier, we treat it as a particle in its own right. And so that electron could have come here and then it would have jumped somewhere else. And now we have 2 holes that are moving around. Okay. All right, let's take a pause. Let me know if you have other questions. Question? Okay. All right, so the value for mu n and mu p is 1420 centimeter square per volts times second. And mu p is less than 50%. So 470 square per volts times S. Okay, far less, almost 1/3. Let's see, limit 48. Now, here's a chart. So laws of physics apply. And what scientists learned was that you could increase the electric field up to a point, but then it would start to slowly saturate. Okay. So here's a chart that shows you the response of carrier drift velocity in response to the applied electric field. Up to a certain point, it's kind of linear, meaning as the electric field increases, the electrons will drift in response to that electric field up to a certain point in a linear manner, linear relationship, right? It's a constant of proportionality. It's proportional, directly proportional. If it increases, drift increases. If electric field decreases, then the drift current also decreases. Now, after a certain point, and this is of course different for different semiconductor material, but a saturation point is reached in every single semiconductor material. If you look at silicon, which is right here, this line, it's linear up to this point, meaning about right there. 2 times 10 raised to 3. 2 times 10 raised to 3 is, let's see, my counting at 2, 1, 2, 3, 3 times. 3 times 10 raised to 3. Okay. 3,000 volts per centimeter. 3,000 volts per centimeter. Even beyond that, I would say starts curving right around here. So maybe right around 4,000 volts per centimeter. Some books might even say 5,000, but I like to say it's about 3,000. Okay, beyond that, we don't know. So about an electric field density of 3,000 volts per centimeter square or per centimeter, the mobility starts decreasing. It's no longer linear. What does it mean? Current is a result of charge carriers moving. If the movement slows down, then the response of the material slows down. If the response slows down, now if an input is applied and the input is switched or changed, then the response time cannot keep up with that change in the input. Input changes in AC. In AC signals, the input changes constantly. How fast it changes is defined as the frequency. So if it changes really fast, at a certain point, the semiconductor material can no longer respond appropriately, meaning there is an upper limit on the frequency operation range of these devices. So silicon, if you have a semiconductor device created from silicon material, there is an upper frequency range beyond which it will no longer work according to its specification. If you have germanium, slightly different. If it's gallium arsenide, it's slightly different. If it's gallium nitride, it's slightly different. So every semiconductor material has its own value of when its response would saturate. And that is because of the parameter we call velocity saturation. Yes. Not directly. Yeah. Yes. Yes. That is also one thing. Yes. Yeah. Yep. So let me write this down. Saturation for silicon is about 3 to 4,000 volts per centimeter. And that places an upper limit on the frequency of operation for these devices. I think the book states 4.5, 5,000, I believe. Okay. I like to use like 3 or 4,000. All right. So we talked about intrinsic material, right? Those intrinsic charge carriers are not sufficient quantity to create any electrical device or electronic device. So what do? Well, we introduce more charge carriers externally. The process of introducing external electrons or external holes into a intrinsic semiconductor material is known as doping. And the process is known as semiconductor doping. Okay. So basically we add external material to drastically increase charge carrier numbers. And we can create a conductor out of a semiconductor. Now, the reason this is important and the reason why we are able to do this and why we do this, not just able to do it, but why we do this is because of control. If we are introducing external impurities or external material into our intrinsic semiconductor material, we can control the amount that goes in. And the amount that goes in is referred to as the dosage. And this dosage is given in atoms per centimeter cube. Okay, atoms per centimeter cube. So we would take external material, we will introduce it into our intrinsic semiconductor material, and we're going to create free charge carriers. Free in the sense they're free to move about. They are not bound to anything. And those elements are typically from the column 3 or column 5 of the periodic table. Column 3 would be boron, column 5 would be phosphorus. Most common ones. And since this is external material, if it's external, it does not belong naturally in that material, we refer to it as an impurity. And the process is known as doping. And the external material is also referred to as the dopant. And the semiconductor, the resulting semiconductor is doped semiconductor. Yeah, I couldn't believe it the first time either. Yeah, but it's referred to as a doped semiconductor. But in general, the word comes from, the roots of the word is because it's something that doesn't belong organically or naturally. we have about 3 minutes left, so we'll go over it, go over and do a brief overview, and then we'll look at it in more detail afterwards. But here's what happens. You have you have column 3 elements, you have column 5 elements, right? So column 5 elements have 5 electrons in the outermost shell. If you introduce it into a silicon lattice structure, it is going to displace a silicon atom. We can remember I said it's a general discussion about semiconductors, but for most part, I'll just refer to silicon, right? So if you introduce a element from the column 5 of the periodic table, it has 5 electrons in the outermost orbit. 4 of those 5 electrons will form covalent bonds with a silicon atom, with 4 silicon atoms, right? It displaces a silicon atom from its lattice structure, occupies that spot, forms 4 bonds with its 4 electrons. And you have 1 extra electron that is left behind, not left behind. There is 1 extra electron that is available to now move around freely. It is not bound to any atom. It's not bound by any covalent bonds. It is a free charge carrier. And it's 1 extra negative charge. So if you introduce a large number of these external impurity atoms into a small space in your semiconductor material, that small space becomes negatively charged or flushed with negatively charged electrons. The overall charge in that material is going to be neutral because that extra electron that is free to move around is balanced by the positive proton that is bound in the nucleus. That positive charge remains in place because it's inside the atom, the nucleus of the atom, but the electron is free to move around and conduct electricity. So overall, it's electrically neutral, but we still say it's negatively charged, right? Because there are lots of free electrons to move around. On the other hand, if we have elements from column 3 of the periodic table, they have 3 electrons in the outermost shell. And when they bond with the silicon atoms, now there is an empty spot, right? Because it bonds with 3 of its neighboring silicon atoms. 1 bond is left open. It's an empty spot. It's a hole. It's a positively charged particle. Okay. And so there are a bunch of holes that are created when you introduce a column 3 element. Again, overall charge is neutral because it's balanced by the negative charge. Sorry, not negative charge, positive charge in the nucleus. So overall, it's neutral. So with that, we'll stop right here, and I'll pick up here again on Friday. Okay. Look at the homework assignments. There's due tomorrow, and then they're due on either Friday or Saturday, the 16th, 18th, or 19th. And then Friday quiz will open at Friday morning at 8 o'clock. Friday quiz will be assessing on the previous Wednesday, Monday, and Friday. And then Monday quiz will assess on the previous Friday, Wednesday, Monday. Sudhir. Hello.